Alrighty. Today, we are joined by Rishi Bommasani, who is the first guest lecturer in Generative AI for Constructive Communication, a class happening at MIT this spring on the evaluation and new research methods brought to the surface by the generative AI advances. So we're super thrilled to be joined by Rishi, who will be talking about holistic evaluation of language models. Rishi is a third-year PhD student at Stanford who is advised by Percy Liang and Dan Jarafsky, and he is instrumental in the Center for Research on Foundation Models, as well as publishing extensively in the NLP community. Thanks so much for joining us, Rishi.
Great. Thanks for the wonderful introduction. My name is Rishi Bommasani. I'm a CS PhD at Stanford. I'm very excited to give this lecture because it resonates with a lot of my work. So today we'll talk about holistically evaluating language models on the trajectory towards evaluating all different types of foundation models. So to contextualize what I work on, broadly, I work on the societal impact of foundation models. And more specifically, I try to establish the basic facts and understanding of how these models affect society, that is, make them more transparent, then think about what types of new ideas we need to add to the mix to better characterize them. And then given that kind of underlying foundation, how can we move forward and make progress and make change in terms of making sure foundation models affect society in better ways? Today, I'm going to talk about HELM, but I thought I'd also point out and try to drive some themes forward that you'll see later in the course that relate to both emergence that Jason will talk about maybe in a couple of weeks, and then I think in 3 weeks' time, Mina will talk about human-AI interaction. Because I think all of these things are very connected and sort of very intertwined to think about them sort of all together. So this is one of these slides you sometimes see in talks with lots of news articles, but I really want to just point out that this space of generative AI foundation models is really the subject of tremendous attention. And before talking about these specific articles, just notice where the articles come from, right? They come from the New York Times, CBS News, MIT Tech Review, right? These are really some of the top publication venues, and they handle major global affairs like world politics, the pandemic. And that's really what the space is becoming, it's becoming a sort of serious topic, not just for researchers and academics, but for society at large, right? So in the top left, I have this New York Times article from when GPT-3 came out, which is now, I guess, a little over 2.5 years ago. And really the space since then has unfolded very quickly, right? So we have, an engineer at Google thinking that language models are sentient. We have Tim Neat and Meg being fired from Google for their work related to stochastic parrots. And we have all kinds of things across the spectrum here, right? We have Jack Clark testifying before the Senate using a language model. We have Stable Diffusion getting lots of attention. And now most recently, we have ChatGPT from OpenAI that is also getting lots of attention, challenging Google's foothold on search. A judge in Columbia used it in part to influence his thinking on court ruling. Ryan Reynolds is using it to write in ads for Mint Mobile, and as of literally yesterday, New York Times is using it to give Valentine's Day messages. So really, ChatGPT is all around. For us in universities, it is definitely affecting education, and that's also been an interesting topic. So foundation models, and specifically language models, are clearly important. Hopefully that is sort of made clear. To drive it home, in NLP research, which is my background, we see language models basically in every paper. If you go to an NLP venue, and maybe even more importantly, they are widely deployed in lots of already important products and in probably even more future products, including from a lot of very well-funded startups these days. So we can gather language models are important, and it stands to reason that we should understand them, but I think the basic claim is that we don't. And this is what we're trying to address with HELM, right? So before talking about HELM, I just want to acknowledge all of the folks that were involved in HELM. It was led with Percy and Tony, who are at the top,
and feature some important contributions from Dimitris, Dilara, Michi, Jan, Deepak, and Tony at the bottom. And it's a huge collaboration of about 50 people. And inside CRFM, which Hope mentioned, which is this effort we built at Stanford. So what did we think was necessary? Well, we thought it was necessary to evaluate these systems because of this important function that evaluation plays in improving transparency and allowing us to understand what's going on, right? So benchmarks we can think of as functioning in two different ways. In one sense, they clarify the current status quo of technology. And in the second sense, they are something that we want to improve upon and therefore affect future technology. And in both regards, it's challenging to get benchmarks and evaluations to design them effectively, right? Karen Spark-Jones, who's a sort of luminary in NLP, gave this quote, "Proper evaluation is a complex and challenging business." And nonetheless, I think this becomes even more challenging when we think about language models, as I'll try to make clear throughout this talk. So, I'm giving a talk and I'll try to explain some of this, but I think an even more useful way to understand language models is just to go to the HELM website and explore all of the kind of models and results and look at the actual predictions they generate, because I think this is actually a really effective interactive way to ground your understanding of this technology. So to make sure we're all on the same page, when I'm talking about a language model here, what I'm going to mean by that is I'm just going to think of any text-to-text interface. So the input is text, the output is text, perhaps the output is assigned probabilities. I'm not really going to make any assumptions on how this language model is built or implemented, right? So it doesn't need to be a transformer, but most of them are. Doesn't need to be autoregressive, but most of them are. And this is largely in part because some of the systems we're going to benchmark are things where we have very little insight into how they're built. And so we're not going to assume much about that. So if the goal is to evaluate language models, one of the questions is like, how should we design that evaluation, and what should the principles be by which we design that evaluation? And I think the key thing to keep in mind here is it's much less obvious than other types of evaluations we become accustomed to in AI, right? So if you think about trying to evaluate an image classifier, well, at least you know the classifier is going to classify images, so you know what task it's going to be used for. Maybe you even know what type of distribution of data you'll encounter. And those constrain the space of how you're going to design your evaluations. Even still, there are going to be design decisions. But with language models, because you can use them for so many different things, and for each of those different use cases, you should sort of desire a bunch of different desiderata. You need to navigate the space. And so this is the sort of first topic we're going to spend some time on in this talk is how do we navigate the space, right? So we think we factorize the space into scenarios or use cases, right? So there are many different ways you could use a language model, arguably infinitely many different use cases. And for each of those use cases, we should care about a number of different desiderata, right? It's important but insufficient to say that models are accurate, right? We want models that are fair, robust, efficient, and so on. And so an important part of HELM is trying to first provide a sort of broad space, the broad taxonomy, and then within it, pick a representative subset that we actually have the resources to evaluate for. And then building on that, we really wanted to make sure we highlighted that for the current state of AI, especially if we're going to think about societal impact, it's insufficient to only focus on accuracy, right? A lot of AI focuses on accuracy, but there are many other desiderata we should care about that are hugely pertinent for society. And we wanted to make sure we evaluated each of those in each specific context, right? So for example, in toxicity detection, right, maybe the trade-off between accuracy and fairness and how we interpret that trade-off is going to be different than the trade-off in sentiment analysis, right? So we want to ground everything in the specific use cases. So if you want a mental model of how does this kind of paradigm for evaluation juxtapose against other evaluation paradigms, I think this is a simple sort of way to think about it, right? So in ImageNet and in the vast majority of AI benchmarks, we're evaluating the accuracy of some model on a specific data set, right? For example, ImageNet. As we get systems that are more multi-purpose or general purpose, we might expand that to evaluate them on a range of different tasks, but still primarily have looked at accuracy. So things like superglue in MLP. And in HELM, we're going to try to expand that across the other dimension. So we're going to not just look at many data sets, and many here is going to be even larger, but we're going to look at many metrics at the same time. And we'll kind of get back to this later once I sort of specify what we evaluate. The final piece is, while language models have been hugely important, and there's been tremendous amounts of research attention allocated towards them, their evaluation is very uneven historically, in the sense that different language model developers evaluate on different data sets at their own discretion. And so it's very hard to compare them, right? Actually, there are even further nuances, like whether you fine-tune the model or prompt it or so on. But by and large, the space prior to this work was very sparse and hard to compare different models against each other. And sort of the point is now we are going to try to get a lot more sort of head-to-head comparisons between models. And there's going to be a bunch of other nuances that I'm not going to really talk about. Some of them I just kind of want to highlight is this idea of train test contamination, right? Because the models are trained on wide swaths of the internet, and for these more recent models that are trained on human data, including data that, for example, OpenAI gets from people querying their system, you want to make sure that what you test on is distinct from what the model has been trained on, and this is kind of hard to ensure. And we're trying to do some sort of policy effort on this front, but I'll not really talk about this. So just to ground it, and again, if folks have questions, just jump in at any point. This is going to be roughly the sort of shape of the evaluation we have. So we have all these different scenarios that span different tasks like question answering and summarization. I'll also talk about these targeted evaluations later. For each of those, barring a couple of exceptions, we're going to measure 7 different metrics. So things like accuracy and calibration, robustness, bias. And we're going to, that specifies the benchmark. Then we're going to evaluate about 30 different models against that benchmark that come from a variety of different providers. And so I think it's important to just keep in mind the scale here, because the scale did influence our decision-making, right? And I think is in general going to be a question when you think about evaluating these models, is there are very material costs, right? Costs about $40,000, and in addition about 20,100 hours, which maybe would price to another, let's say, $20,000 or so $1,000. So I think this is an important factor, right? Especially when we deal with models that are much larger and are compute intensive, not just to train, but to do inference on. We need to navigate those costs intelligently. So now I'm going to try to dive deeper into exactly how did we evaluate and then try to get to the results. So to think about it, a language model, as we're understanding it, is a text-to-text interface. So I need to specify for a given scenario, a given use case. So for example, think about the IMDb data set, which is a data set of documents or reviews where you want to say the sentiment of those reviews. How are you going to use the language model to do that? Well, you're going to take the individual instances, the individual reviews in this case, and somehow adapt them, that is prompt in this case, the language model, so that you can get the language model to produce a prediction. And then given those predictions, you're going to measure some kind of metrics, like how robust are the predictions or how accurate are they, or so on. Right, so that's the kind of, those are the pieces in play, right? And then I'm going to talk about what are the scenarios, what is the adaptation method, what are the models, and what are the metrics. Right, so the first one, scenario, is you can just think of it as a bunch of instances, which are roughly, machine learning speak XY pairs. And these can have different formats, right? Some scenarios, maybe there are different answer choices of which one is correct. Maybe other scenarios, for example, on text summarization, there's just the input document and what the reference summary, but there's no alternative choices, right? So these will differ based on specific tasks. Then how do you adapt the language model to do this? I think this is an important nuance because you have a lot more degrees of freedom than you do in other types of machine learning, right? The sort of fluidity and expressiveness of language as an interface means you can do things in a variety of different ways, right? So here are two different ways to do multiple choice question answering. On the left, one way you can do it is you can give the language model a question, give it the answer choices, ask it to generate an answer, and then see of the 4 answer choices, which one did it predict and as most probable. So that's one way to do it. But another way to do it is you could give the model the question and then put in one of the answers, get it to assign a probability to that, do that for the other 3 answer choices and see which one it assigned the highest probability to, right? So this is just a different way to query a language model to do this very same problem, but you might get considerably different answers. And as we'll see, for some models, you get dramatically different answers, and this makes it hard to know how much you should trust the evaluation results. And then finally, for the metrics, we're just going to compute a bunch of different metrics, right? So calibration, robustness, fairness, runtime, and so on. So now let me talk about how we made decisions for each of those before I get to the results. So the first part we need to make decisions on is what concrete scenarios are we going to actually evaluate on, right? And so remember that there is this kind of vast space, right? And so we structure the space into these 5 categories, right? So we think of what task, sort of the abstract mapping from X to Y are we trying to do, right? So question answering, you're taking a question, produce the answer. Sentiment analysis, you're taking a document, producing sentiment. Now that abstract task is grounded in specific data, right? And that data distribution has properties like who wrote that data, what is the kind of genre of that data, and so on. And then finally, there's an additional dimension that we mostly don't think too much about in HELM, at least in the initial version that I'm mostly going to talk about, which is what language is all of this posed in, right? So mostly we're evaluating models that are predominantly English-based, and so we're going to evaluate them on English data. But there are many other world languages, and we're increasingly seeing language models for other languages, including multilingual ones. And so this is also an area for improvement to get evaluations of similar rigor for languages beyond English. So that's how to think about the space. How are we going to actually arrive at the subset of the space that we can reasonably evaluate, right? Because we certainly do not have the resources to evaluate everything. So one thing is we wanted to sort of enumerate what are all of the possible paths, what are all of the possible genres and so on, so that we could meaningfully pick a subset from them and know what we were including and therefore also what we were excluding and be intentional about it. So what we came up with, because it's kind of hard to know how to do this, is we try to use some existing resources. So one existing resource, which maybe people who've done some NLP might encounter, is when you submit a paper to an NLP conference, they have these tracks. So that's the kind of left column, tracks like ethics and NLP or information extraction. In each of those, we had some NLP researchers expand that out into the tasks that are well studied within each of those tracks. And so that gave us the collection of tasks that we could possibly evaluate for. And then we decided to pick a subset of those tasks. And the constraints we imposed were we wanted tasks that were unilingual, so only in English. For example, we don't do any machine translation. We want tasks that were unimodal, because we're using language models. So we don't do any image captioning, for example. And then the maybe most opinionated choice was we thought about what tasks are more user-facing, right? And this is definitely a subjective judgment. And this is mainly because we were trying to think about sort of direct social impacts. And so we're kind of focusing on user-facing things. And so we arrived at these 6 final task categories, which are the ones that we, at least in the first version of HELM, implemented. Since then, we've added some other tasks and so on. one thing I kind of want to point out is as language models have been deployed, we've seen that they actually have a lot of use cases that have no real relationship with tasks the NLP community has studied historically, right? For example, OpenAI has this kind of all of these little icons of different ways people use the OpenAI API. Most of these have no history of study in NLP, at least to my knowledge, or they're not mainstream by any means. Nonetheless, they are ways language models are being used and affecting people. And so we're trying to figure out new ways to capture some of these as well, because they have no existing benchmarks. But that's very much in progress at the moment. So to ground it, there's a typo. This should say RAF, not CivilComments. But this is, for example, one of these. So this is text classification set where have people asking questions about banking, and the model needs to predict the correct label out of 77 choices about what kind of banking related event is this associated with. Okay, so that's how we picked the task. I didn't tell you fully how we got to the exact scenarios, but I'll skip that for the sake of time. Now, let me do it on the side of the metrics, right? So the first thing we thought was, okay, let's try the same process. Let's go see what people in the NLP community and NLP conferences paying attention to. And definitely people are thinking about more than just accuracy in NLP, but we were sort of dissatisfied with what people in NLP were primarily thinking about. So of course, all of these conferences have people working on other things, but we thought it would be better if we really tried to cover all different types of AI conferences that represent different perspectives in AI and different sub areas. So we took a list of all of the AI conferences, expanded it out into the Desiderata that have been, to our knowledge, well studied in those conferences. And then the union of those, the thing at the bottom, is this list of about 37 Desiderata that one could have of AI systems. Right now, I'm sure there are more, and I'm sure a lot of these differ, like in how you interpret them. But we took this 37 and then tried to think about which ones could we reasonably evaluate for, right? So if you recall, one of the assumptions we made is we're really not going to assume any kind of knowledge about how the language model is constructed, because in practice, in many cases, that's what we have. So we discarded. So we first tried to taxonomize all of these different desiderata, which ones require more knowledge about the language model and which ones don't. And the ones that we'll finally evaluate on in the bottommost row are precisely those where we didn't really need any additional information and thought we could directly evaluate for them, right? So it's going to be this 7 or so. Right, and as an example, I'll talk about calibration here as one of these metrics. So in calibration, what you want is you want the model to assign probabilities that are calibrated with its behavior, right? So for example, if the model assigns a probability of 0.4 to the correct answer, to an answer, 40% of the time that should be the true answer of those instances. And so similarly, for each of these abstract desiderata, you need to specify a concrete metric. I'm going to skip that, but there's some discussion in the paper of why we made certain decisions. So the TLDR is you arrive at this kind of matrix, right? So on the rows, you specified what are the use cases you're going to care about. On the columns, you specified what are the desiderata and metrics you're going to evaluate for. And then we're really trying to get every possible combination. In some cases, that's not really possible, right? For example, if the model doesn't have to generate text, you can't assess if the text is toxic. But by and large, we really fill out this kind of space. The final point I want to make is we did all of this, trying to think about this holistic picture of societal impact and whatever. One further thing is, I think that's great for having this kind of nuanced, everything put together kind of view. I think it's also useful to have kind of more isolated evaluations of specific things that are trying to really isolate out that specific thing and remove any other kind of factors, right? So you can more easily understand things. So we did that for a range of different factors, right? So in terms of capabilities, we looked at language understanding, knowledge, and reasoning. And in terms of harms and risks, we looked at copyright and disinformation risks. So the likelihood of generating copyrighted content or how the model could be used by a disinformation actor to generate disinformation, and also some stuff on bias and cases. So if you've kept some kind of mental model of that in mind, roughly what you should think of is that I sort of specified like what the benchmark is, like what are we going to evaluate a model against. Now, let me just tell you something about what the models themselves are. So these are 30 models, and since we've added, I think maybe 5 or 6 more as new models come out, and that come from 12 different organizations, right? So there's places like Google and OpenAI and Microsoft and Meta and Anthropic and Big Science and so on. These are predominantly models for text. There's a couple that are for code predominantly. They all actually tend to be fairly similar in how they're constructed, right? They tend to all be transformer based. They tend to have kind of autoregressive factorizations, sort of do next word prediction. They vary significantly in their size. The largest model, Turing NLG from Microsoft, is about 500 billion parameters. And the smallest model is probably like 1 billion parameters, or actually maybe even smaller than that, or 500 million parameters. So there's a kind of good range in terms of size. And a key piece here is that the access to these models differs. And this is an important matter because obviously you cannot evaluate things you cannot access. So some of these are behind commercial APIs. So it takes money to pay to evaluate them. And some of them are closed. So we had to convince the model provider, so Anthropic and Microsoft, to give us access to evaluate these. And we're doing something similar at the moment for Google and DeepMind. And this is the kind of compute it took to evaluate. I'm going to skip the prompting details and see if anyone has questions about them later, and just try to get into the results in the final few minutes. So, one of the first questions that I often get is like, oh, well, what's the most accurate model? So here it is. So in the top left figure is ranking the models based on accuracy. There's a little bit of nuance here because, you have to ask the question accurate on what, right? Because we're evaluating on a bunch of different data sets. So we have this kind of way of aggregating across data sets of like, if you randomly picked a data set, what is the win rate of, or what is the extent to which the given model will do better than the other models? In social choice theory, this is called the Borda condition. So by accuracy, the top model is Text DaVinci 002. Since then, we've evaluated Text DaVinci 003, also from OpenAI, which is very similar in terms of accuracy. And the other top 2 models are Anthropic and Microsoft's largest models. One of the interesting things then is to go beyond accuracy, right? This is, the spiel I've just argued for, is that we should care about more than just accuracy. And really understand how are these metrics related to each other, right? So let me first talk about the relationship with accuracy. One of the interesting things, which has been seen in other areas, in other contexts, is this kind of on-the-line phenomenon. So if you look at the robustness of the center top figure and fairness, the right top figure, you see that there's they're very clearly on the line, close to the line, meaning that accuracy and fairness and accuracy and robustness are very strongly correlated. This is kind of interesting to see. The accuracy robustness type of thing has been observed before. The accuracy fairness one was actually a bit surprising to us. Kind of interesting to think about. But also other metrics don't kind of pattern the way we would have intuited. So for example, accuracy and inference time, you might think the largest models, for example, will be the slowest, but also the most accurate. But you don't really see a strong anti-correlation between inference and time and accuracy. And one of the nuances here is that inference time is not only affected by the model size, but also based on the amount of compute the provider puts behind it, right? So for example, some of the largest models also have the most compute behind them, so they're actually quite fast. Like one of the interesting things is like, if you look at OpenAI's models, like their largest models are sometimes faster than their smallest ones in wall clock time because there's more compute behind them. So we have some follow-up work that tries to the extent possible, deconfound that, but it's a little bit challenging. And then finally, for other things like accuracy and calibration, or accuracy and bias or toxicity, the trends are kind of very hard to sift out. And in the paper, we have some finer grained discussion. Another thing you might wonder is how have things changed over time, right? These models didn't all magically appear. They were released different points in time. And for example, how has, say, the accuracy on different data sets evolved as a function of time? So what I'm plotting here is the accuracy of the most accurate model at any given point in time on that data set. And what you see is you see this large spike early on in 2020, May 2020, when GPT-3 came out. And then for some data sets, you see later spikes, basically around Anthropic's model release and the more recent kind of Instruct GPT type models being released by OpenAI. But for most of the data sets, the other model releases are not contributing more accurate models. Really, the kind of most accurate models for most data sets are from OpenAI and Anthropic and maybe Microsoft. And this bears out in this plot, which is about how does accuracy, and we have similar things for other metrics, pattern as a function of model access, right? Especially as researchers, we might especially care about models that we can actually access. And it seems like there is usually a kind of gap between models that are open in the blue and those that are limited or closed in the orange and green. And this is largest, for example, on truthful QA, you see this very large disparity between limited models, so those from OpenAI in particular in that case, and open ones. It seems, especially for knowledge-intensive and reasoning-intensive things, that the gap is larger, but for other things, the gap is small, right? For example, for IMDb, actually the open models are the most accurate by a very razor-thin margin. Another thing I'm going to kind of skip is like how much do these results vary based on different factors, right? So how do they vary as a function of the specific choice of in-context examples you picked, or the randomness involved in that selection, or the number of in-context examples. There's a lot of fine-grained results here. I think one of the interesting ones we have a follow-up paper on is the CNN Daily Mail one, where you see that actually the curve is not monotonically increasing. That is, adding more and more in-context examples actually hurts between the 0 to 1 case. And what we kind of observed there is actually the human authored reference summaries, the ones you would put in context, are actually tend to be worse than machine generated summaries when evaluated by experts. So that's a kind of interesting thing to think about when we think about sort of benchmarking summarization in general. And then finally, going back to the point I made in the very beginning, right? You have these different ways that you can use a language model to do the very same kind of task or data set, right? For example, how do you do multiple choice question answering? You can have a variety of different approaches. I think the most important thing to take away from this is that the choice of approach can have a profound impact on the results, right? So for a given model, so a given set of 3 bars, you see sometimes the gap between the most accurate approach and the least accurate approach can be like 50+% in accuracy. And further, you might hope that at least like the best approach for a given data set holds across all models, but that's also not really true, right? The relative ranking of the blue, orange, and green is not the same across within a plot across all the different columns. So yeah, I will maybe just conclude with 2 points about human eval, and then folks can ask any questions and so on. We did sort of fairly large-scale human evaluations for text summarization and disinformation generation because we weren't super satisfied with the automatic evaluations that existed. So I think the key takeaway in this plot, in this figure, is that if you look at the bottom, human generated, it actually gets much lower scores. So it's one thing we kind of compared that we didn't really expect to be that informative, but turned out to be actually very informative, is if you get humans, so for example, crowd workers or also human experts, like freelance writers, to evaluate the existing summaries in these data sets, so the ground truth per se, they actually get much lower scores than the machine generated summaries, right? Across the board, right? This is for faithfulness, coherence, a number of different things, right? And this is super concerning because, it doesn't really make sense to ask the models, to test how similar their summaries are to a summary that's actually worse than theirs. So I think we're going to need some more sophisticated evaluations for summarization than what we've looked at over the past decade. For disinformation, which is a risk that often comes up, like people have talked about the potential for misuse of language models to generate political disinformation or other forms of disinformation. We looked at two things. So first, can language models be used to reiterate disinformation content, right? So can a disinformation actor capitalize on the scalability with which models can generate content to reiterate their content many times? And turns out models seem to be pretty good at this under human evaluations, especially the text image 002 and Anthropic's model, perhaps. One thing the models are less good at, though there's actually a more recent paper from Johannes Eichstadt's group at Stanford that maybe contradicts it with more thorough experiments, is can the models be used to change behavior, right? So for example, in this wedging task, models were asked to generate divisive content to convince people to vote differently. And in our evaluations, it seemed like models were not that great at that. But actually, in some of Johannes's work, if you look at finer grained phenomena, actually maybe there's some further concern, further reason for concern on that front. So yeah, that's where we are. We're working on a bunch of different fronts moving forward. But yeah, I'll stop here and see if folks have any questions.
Thank you so much. Rishi, Siyash is going to lead our discussion, but thanks so much for giving us such interesting insight into your work and connecting it to a lot of the themes that we started talking about last week. So
yeah, thanks so much, Rishi. This is fantastic.